Welcome to the part 5 video on Computer Vision, Unit 3 Feature-Based Alignment and Motion Estimation. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. In motion estimation, we have 5 different techniques: translational alignment, parametric motion, spline-based motion, optical flow, and layered motion. We can see one by one. The first one is the translational element, and in this we have many parameters which you use for measuring this translational element, and you estimate the motion from these parameters. Then we have the error matrix, SSD, that is sum of square differences, sum of robust differences, SRD, sum of absolute differences, SAD, weighted or windowed SSD function, weighted, sum of squared differences, and root mean square intensity, error, RMS, bias and gain BG, cross correlation CC, normalized cross correlation NCC, and normalized SSD score, which is NSSD. So these are the different parameters which you use for calculating it. So translation alignment, which is the simplest way, shift one image relative to the other and find the minimum of the square, sum of the squared differences, that is the SSD function. This is the equation of it, where U equals U comma V, which denotes the displacement, and E is the residual error or displacement frame difference. And in practice, a bilinear interpolation is often used, but bicubic interpolation can yield slightly better results. The assumption that corresponding pixel values remain the same in the two images is often called the brightness constancy constraint. And in robust error matrix, that is robust outliers, this is the equation for ESRD, and robust norm, which yields that E is a function that grows less quickly than the quadratic penalty associated with least squares. And one such function is sum of absolute differences, ESAD, and this is not well suited to gradient descent approaches. In the error matrix above, we ignore the fact that for a given alignment, some of the pixels being compared may lie outside the original boundaries. So spatially varying weights, we may want to downweight the middle part of the image, which often contains independently moving objects being tracked by the camera. So weighted or windowed SSD function equation is EWSSD of U is given, where the weighting functions are W0 and W1, which are 0 outside the image boundaries. If a large range of potential motions is allowed, the above metric can have a bias towards smaller overlap solution. So the windowed SSD score can be given by the overlap area. So this is the window equation. And root mean square intensity error, RMS, will be equal to square root of EWSSD divided by A. That is your overlapping area. And bias and gain exposure differences, the two images being aligned were not taken with the same exposure. Bias and gain model equation is given here, where alpha is the bias and beta is the gain. And EBG equation is given. The linear regression is needed to find the parameter. Cross correlation. Taking the intensity differences is to perform the correlation, that is to maximize the product or cross correlation of the two aligned images. If a very bright patch exists in the I1 of X, then the maximum product may actually lie in that area. So this is the equation for ECC, that is for cross correlation, and this is for ENCC. Where your I0 and I1 are the mean images of the corresponding patches, and N is the number of pixels in the patch. The normalized cross correlation score is always guaranteed to be in the range of -1 to 1, which makes it easier to handle in some higher level applications, such as deciding which patches truly match. And normal correlation works well when matching images taken with different exposures, example when creating high dynamic range images. So a variant of natural cross correlation which is related to the bias gain regression implicit in the matching score, is the normalized SST score. So which is the equation here, ENSST. The next is the hierarchical motion estimation. And in hierarchical motion estimation, we have a well-defined alignment cost function to optimize. So how will we find the minimum of it? So the simplest solution is to find a search over some range of shifts. This is often the approach for block matching in motion compensated video compression. So to accelerate this search process, hierarchical motion estimation is often used. The motion estimate from one level of the pyramid is then used to initialize a smaller local search at the next finer level. This is the picture of it. The pyramidal structural image, that is level 0, each level you take up the images, and this is the arrangement of it. So here in the level 0, the images will be very coarser and we have very least resolution. So as you move up, the resolution will reduce and the picture will be very coarser. And as you move down, the picture will be very fine and the resolution will be very high, which will increase the resolution. So for level 0, you have a 1x1, here a 2x2 level of pixels. So similarly, the last level, we have n×n images. The next technique is Fourier-based alignment. So when the search range corresponds to a significant fraction of the larger image, the hierarchical approach will not work well. So we have to go for the Fourier-based alignment, and the equation is given for the image I1 of x plus u. And the Fourier transform of the cross correlation function ECC, which can be written, and this is the f of ECC for a cross correlated images in spatial domain. So we take the Fourier transform of both the images I0 of x and I1 of x, multiply both the transforms, and once you multiply both the transforms together after conjugating the second one, so you conjugate I1 star of omega. After conjugating it, and take the inverse form of the result. Fourier-based alignment, consider the SSD formula and the Fourier transform for that is written, and the SSD function which can be computed by taking twice the correlation function and subtracting it from the sum of energies of the two images. So take the sum of the squares of individual images and subtract the twice of the product of the two images in Fourier transform. Windowed correlation. The Fourier convolution theorem, which applies only when the summation is over xi and is performed over all the pixels in both the images. So it makes no sense when the images overlap by a small amount or one image is a small subset of the other. So W0 and W1 are the valid or 0 outside the valid ranges of the images. The images I0x and I1x. And circular shifts, it will return 0 values outside the original image boundaries. Next is about the phase correlation. The spectrum of the two signals being matched is whitened by dividing each per frequency product by the magnitudes of the Fourier transforms. So you take the product of it and you divide it by each frequency component, that is the Fourier transform of the individual images. So you can get the phase correlated details of that image. In the case of noiseless signals, then we will be having I1 of x plus u will be equal to I0 of x. So this is the conclusion when you have a noiseless signal. So the output of the phase correlation is a single spike located at the correct value of u. Consider the two images, rotations and scale. You consider two images that are related purely by rotation. So I1 of r cap of x will be equal to I0 x. So if we resample the images into polar coordinates, so this is the representation of it. And if the two images are also related by a scale, so scale factor will be introduced, then that is your ES cap. So you can resample into log polar coordinates, and the equations are given here. For images that are also translated by a small amount, so you have rotation, scaling, and now translation. So R cap denotes your rotation, S cap denotes E power, X cap it denotes the scaling, and now T denotes your translation. So two images are aligned in rotation and scale using the polar or log polar representation. Once rotation and scale are estimated, one of the images can be de-rotated and scaled, and a regular translational algorithm can be applied to estimate the translational shift. So unfortunately, this trick will apply only for the images having large overlap, that is having very small translation motion. Next is incremental refinement, and in general, image stabilization and stitching applications require much higher accuracies to obtain the acceptable results. So a more common approach is used to gradient descent, which uses the Taylor series expansion, and the ESST equation is given. And in incremental refinement, this is the equation for the Jacobian, that is image gradient for Jacobian, and this Lucas and Kennedy equation. Incremental refinement, so your optical flow constraint or brightness constancy constraint equation has been given, where your Ix and Iy denote the spatial derivatives and It denotes the temporal derivative. And when squared and summed or integrated over a region, it can be used to compute optic flow associated normal equation. So this is the final equation, and this is the Hessian equation for value of E. And these are the equations for the ESST. After solving everything, we've come to the conclusion. This is the final optical flow constraint equation. There is Ixu, Iyv plus It. It denotes your translation. So this is Jacobian matrix. Jacobian of the Hessian matrix, that is del F will be equal to Hessian matrix of F. So H of X is the Hessian matrix. And incremental refinement, where your Hessian equation and gradient weighted residual vector B, and E will be the error, and Ix, Iy denotes the spatial derivatives, and It denotes the temporal derivative. So this is the representation of A and B in terms of Ix, Iy and It. So conditioning and aperture problems, the component of the displacement along the edge is very poorly conditioned, and it can result in wild guesses while small noise perturbations are present. So one way is to mitigate this problem is to add a prior soft constraint on the expected range of motions. So this is the picture for conditioning and aperture problems. And for uncertainty modeling, the reliability of a particular patch-based motion estimate, it can be captured more formally with an uncertainty model. The simplest model will be a covariance model, where you add small amounts of Gaussian noise, then the covariance matrix will be proportional to the inverse of the Hessian. So Hessian A, so A inverse is given. So sigma n square will be the variance of the additive Gaussian noise. So applying the LK update rule to follow the metrics, so we are using bias and gain model, then weighting of your LK model, and then robust error matrix. So the corresponding equations for bias and gain model, that is ELKBG, and weighted version of LK model, that is ELKWSST, and this is the LK model for robust error metric. And parametric motion, these are the sum of the basic set of the 2D planar transformation which we saw in the first part of the video itself. So these are the sum of the examples for the translational motions transformation. The next technique is parametric motion. And in parametric motion, we use these translational transformations for different applications, and the affine which has been given. So instead of using a single constant translation vector, you use a spatially varying motion field or correspondence map. So correspondence map is x dash of x comma p. And in the parametric motion, the modified parameter incremental motion update rule is given, and this is the parametric motions LK model equation, where your Jacobian has been given and the image gradient. So this is the Hessian and gradient weighted residual vectors for this model. Next topic is patch-based approximation, where your computation of Hessian and residual vectors for parametric motion can be more expensive than for the translational case. So for parametric motion with n parameters, small n parameters and capital N pixels, the accumulation of your Hessian and the error B, which will A and B should take n square into n number of operations. So to reduce this, one way to reduce this by a significant amount is to divide the image. So you have to divide the image up into smaller sub-block patches Pj and to only accumulate the simpler quantities 2 cross 2 quantities inside the square bracket. So your Hessian and gradient level A and B which has been given, and this Hessian and residuals which can be approximated, and approximated equations are given. So in compositional approach, for a complex parametric motion such as a homography, the computation of motion Jacobian becomes complicated and may involve a per pixel division. So simplification is, first wrap the target image I1 according to the current motion estimate x dash, and then compare this wrapped image against the template I0 of x. And in inverse additive algorithm, replace this gradient I1 tilde of x with the gradient of I0 of x, which will allow the pre-computation and inversion of the Hessian matrix. So the residual vector B, which can also be partially pre-computed, the steepest descent images, which can be pre-computed and stored for later multiplications with the E of x, that is the error images. So this is called as the inverse additive scheme. So you take the inverse and add it up with the template I0. So in inverse compositional algorithm, wrap the template image I0 of x and then minimize, because the inverse compositional algorithm which will have the potential of pre-computing the inverse Hessian and steepest descent images, which makes it the preferred approach. So it has the advantage of the Gauss-Newton iteration also. Next is the learned motion model. So first a dense motion model is computed from a set of training video, and SVD is applied to the stack and motion videos, and then compute the first few singular vectors. So for the new test sequence, a novel flow field will be computed from coast to fine algorithm, and this is the equation for it. So this is the picturization of a learned parameterized motion field for a working sequence. And the application of them is, first one is the video stabilization. So here 3 major stages of stabilizations are there, and motion estimation, motion smoothing, and image wrapping. So in motion estimation algorithms, you lock on to the background motion, which is a result of camera involvement without getting distracted by independent moving foreground objects. So your background remains the same. So only the foreground which move from here and there has to be estimated. So motion smoothing algorithms which will recover the low frequency, that is slowly varying parts are low frequency parts of your images, and this of the low frequency part of the motion will be recovered and estimate the higher frequency shaking component, that is highly moving components, that needs to be removed. That is your motion smoothing algorithm. And finally image wrapping algorithm, which apply the high frequency correction to the render the original frames as if the camera had undergone only the smooth mesh. So you are warping the images with the smooth motion alone, and high frequency components will be rectified. Next is spline-based motion. So spline-based motion, traditionally we have the optical flow algorithms which will compute an independent motion estimate for each pixel. That is, the number of flow vectors computed is equal to the number of input pixels. The general optical flow, which will be analog, can thus be written as the given equation, which will represent the motion field as a two-dimensional spline controlled by a smaller number of control vehicles. And this is the basic functions, where your bj will be the basis functions, and non-zero, which is over a small interval alone, it will be non-zero, and the weightages wij for the basis functions to emphasize your ui and the linear combination of the uj cap. So some of the spline basis functions are block, then linear square pixels, and then linear triangles, then bilinear and biquadratic, which are the some of the examples for spline based motion. So this is a representation of spline motion field, the displacement vectors ui, comma vi, and which are shown as pluses, all the plus indicated, and some of the controls uj cap, which are shown as circles. So these are here all these circles which are shown are here uj caps, which are the orthogonal to that. Then quadri spline based motion picture has been given, and how they are represented, how they are tracked, and how they are convolved. So disadvantage of the basic technique is, that is, it has a pure job near motion discontinuities unless an excessive number of nodes are present, and large cells are used to present the smooth motion, and smaller cells are added in regions of motion discontinuities. The next application is medical image registration, and the picture of that is produced. And another example for octree spline based registration. The next technique is optical flow. So optical flow is the most general and version of motion estimation, where you compute an independent estimate of motion at each pixel, which is generally known as optical flow. And the equation for optical flow is being given ESSTOF. And after each iteration of the optical flow estimation in a coarse to fine pyramid, they rewrap one of the images so that only incremental flow estimates are computed. So when overlapping patches are used, an efficient implementation have to be done, which compute the gradients and intensity errors. So this is the equation for constancy constraint, that is the linear brightness, that is your EHS, where this is your IT will be the temporal derivative, and EX and EY are your regular image coordinates, and U and V are the 2D optical flow functions. So this picture, it shows the iterative coarse to fine optical flow estimation. So your class variational energy minimization approach, and the next one is the recent neural network approach with the optical flow. So in coarse to fine optical flow estimation, we have two images, image I and image H. Then the Gaussian pyramid of it, which will be built from fine to the coarser level. So Gaussian pyramid of your image H and image I, and then we have the number of pixels being reduced from the bottom to the top. So you frequently run the iterative LK Luna's Cano-K method, and after that you wrap and warp and sample it. Then again you perform the iterative LK in the next image. So similarly you do it for all the layers present in this Gaussian pyramid. So in top level, apply LK to get a flow field representing the flow from first frame to the second frame. Then again flow field will be applied and warp the first frame towards the second frame. Then return to the LK on new wrap image to get a flow field from it to the second frame. So repeat till you get converged. And next level, when you go, you have to upsample the flow field to the next level and first guess the flow at that level. Then apply it to first frame and then to the second frame. Similarly, you do it for till in all layers till you get converged. Next is multi-frame motion estimation. So motion estimation is considered as a two-frame problem where the goal is to compute a motion field that aligns pixel from one image with those in the another. But in practice, it is usually applied to video where you have sequence of frames which will be shown for a single second, that is 60 frames per second. So one classic approach to multi-frame motion is to filter the spatiotemporal volume using oriented or steerable filters. So because the pixel motion is mostly horizontal, slopes will be having the pixel tracks and which correspond to the horizontal velocities. So spatial temporal filtering uses a 3D volume around each pixel to determine the best orientation in space-time, which corresponds to the pixel's velocity. And the diagram shows the spatiotemporal volume. And the applications are video denoising and deinterlacing. So video denoising, which is the process of removing noise and other artifacts from the film and video. So unlike a single image denoising, we also have information available only in the current picture. So video denoisers can average or borrow information from the adjacent frames. So deinterlacing means video deinterlacing is the process of converting a video taken with alternating fields of even and odd lines to a non-interlaced signal that contains both fields in each frame. Then the last type of motion estimation, which is your layered motion. So here in many situations, visual motion which can be caused by movement of a small number of objects in different depths in the scene. So in such cases, we go for more succinctly explanation of your pixels that are grouped into appropriate object or layers. And this is caused by translational motion of checkered backgrounds and rotation of the foreground hand. And complete motion sequence can be reconstructed from the foreground and background elements, and they are represented as alpha matted images, which are also called as sprites or video objects. And the parametric motion which corresponds to each layer. So displacing and compositing these layers in back to front order recreate the original video sequence. So this is the picture by layer. So how you estimate the motion from the each image pictures. So layered motion estimation not only lead to compact representation but also exploit the information available in multiple video frames. And also it can accurately model the appearance of pixels near motion discontinuities. So this makes them particularly suited as a representation for image-based rendering as well as object-level video editing. So this is the results of the layered motion estimation. So first estimate the affine motion models over a collection of non-overlapping patches. Then cluster these estimates using K-means. Then alternate between assigning pixels to layers and recomputing the motion estimates for each layer using the assigned pixels. Layers are constructed by warping and merging the various layers pieces from all of the frames together. The motion of each layer is described using a 3D plane equation plus per pixel residual depth offsets. That rigid planar motions homographies are used instead of affine motion models. The final model refinement re-optimizes the layer pixel by minimizing the discrepancy between the re-synthesized and observed motion sequences require a rough initial assignment of pixel to layers. So how you represent the motion using block-based motion prediction and breaking the image sequences into layers, and the advantages which can represent occlusions and disocclusions. Each layer's motion can be smooth video segmentation for semantic processing. These are the advantages. And disadvantages, how will we determine the correct number and how you assign the pixels and how you model the motion. These are the difficulties you face with the layer motion. So the first application is frame interpolation, where this is the final color value of the pixel as a linear plane. So here you estimate the motion obtained at the location in an image, which is obtained at as flow vectors which are said to be reconsistent. So this is an representation of it. Second application is transparent layers and reflections, where this is a special case of the layered motion which occur mostly in transparent motion cases, which is usually caused by reflections seen in the windows or the picture frames. So at the background what you have the reflections in the mirrors like that. The third one is a video object segmentation, where you segment the pictures. This is a example of it. And next is video object tracking. So the block diagram for how you track and what are the steps you include for object tracking. So thank you. This is the end part of your fifth part of the unit.